Flying past the Earth at this time, we see a vast gray ocean beneath a red-tinted sky, punctuated by volcanoes and small land masses. And unlikely as it seems, life may have gained a foothold already. That life in the oceans that gave birth to it may actually be vaporized many times by cataclysmic bombardments, which have slowed but not yet stopped. Earth has begun to take on its final form, a crust, a skin so thin it would be less than a sheet of paper were the Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, two cores, a liquid iron core pulsing out a magnetic field that helps shield us from a deadly cosmic wind from our sun. And a solid nickel and iron inner core. By now, the remarkable process of plate tectonics has kicked into gear. Though how and when it started exactly, we do not know. For what follows next, you might want to strap yourself in. It's going to be a bumpy ride. Here's how it might have happened. At first, Cretans and one continent called had the planet all to themselves. Then, around 500 million years later, Antarctica took shape. About another 500 million years passed before Atlantica formed. The continents roamed separately until, about 1.8 billion years ago, Antarctica collided with what is now Eastern Antarctica to form Nina. Then Nina, Atlantica, and collided 1 billion years ago, forming the supercontinent Rodinia. After about 300 million years, the three landmasses separated and came back together in a new configuration, Pangaea. Pangaea came apart too. When Pangaea split, and Atlantica split up too. If you're confused, join the club. Even the Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close. Run the Earth time machine backwards, and you can see why. But no matter how many times you run the demolition derby of the continents, a question remains. What the hell is driving them? Hell, apparently. The force driving the plates is the slow movement of the super-hot semi-solid mantle that lies below the rigid plates. Like hot soup, magma boils in slow motion. Superheated magma rises to the surface, begins to cool, and then sinks back down to the bottom of the pot, where it is reheated and rises again. This cycle is repeated over and over to generate what scientists call a convection cell, or convective flow. But where's the heat source keeping our earthy soup performing its circular gymnastics? Well, most of it is left over from the spectacularly energetic collisions and gravitational crushing that created the Earth to begin with. It's still trapped down there, and it wants out. And there's something else in the molten depths that makes it pretty hot real estate. Radioactive material. The belly of the beast has plenty of uranium and other radioactive elements, all of which release heat as they decay. That decay has significantly slowed the rate at which the Earth is cooling. So what does this mean at the surface? Two things. First, magma being burped up along the ridges, those places like Iceland where the Earth is tearing itself asunder, is pushing the plates in their respective continents apart. Second, what goes on at the other end of those plates, the collision zone, may be equally important. Here, where the heavier plates dive under the lighter ones, yanked downwards by gravity, they haul along their plates back into the oblivion of the mantle. That's what we know. or what we think we know. But the details of what's going on in the deepest parts of the Earth that drive the engine of plate tectonics, we may never know.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption.
According to the theory of plate tectonics, the lithosphere is composed of several large plates that float on the asthenosphere, which is the liquid layer in the Earth's mantle. The plates move as a result of convection currents in the Earth's mantle under the lithosphere. Convection is the movement of liquid material that is heated from underneath, rises and cools on top. Hot material has a lower density and rises, while cold material has a higher density and thus sinks. Where hot material flows upwards and outwards, the plates slide past each other or separate. Where cold material sinks to the bottom, it pulls one of the plates down with it.
The most common type of divergent plate boundaries are ocean-to-ocean divergent boundaries. These boundaries usually occur along mid-ocean ridges. This is where new oceanic lithosphere is created. As this is where seafloor spreading begins, these areas are called spreading centers. These boundaries form when two plates begin to move away from each other. Divergent boundaries appear along mid-ocean ridges in the ocean and across rift valleys in northwestern Europe and East Africa. The picture you are looking at is the Great Rift Valley in Africa. When a continental-to-continental divergent plate boundary forms on land, it can literally tear a continent apart. When the lithosphere begins to stretch, the two plates begin to separate. Hot rock then rises from beneath the Earth's surface. This causes the crust to weaken. When magma reaches the Earth's surface, a rift valley is born. Some examples of rift valleys are the Rhine Valley in northwestern Europe and the Great Rift Valley in East Africa. The picture you are viewing is a diagram of a continental to oceanic plate convergent boundary. When the continental lithosphere converges with the oceanic lithosphere, the continental lithosphere remains floating. The oceanic lithosphere sinks to the asthenosphere. When the oceanic lithosphere begins to reach a depth of 100 to 150 kilometers, the asthenosphere begins to melt. When the asthenosphere begins to melt, magma forms. The newly formed magma, which is less dense than the mantle, rises to the surface. Eventually, the magma can reach volcanoes where it will erupt. These types of plate boundaries are commonly found in the Andes in South America and at the boundaries of the Nazca Plate. The picture you are currently looking at is an example of a continental-to-continental convergent plate boundary. In a continental-to-continental plate boundary, the oceanic lithosphere is still involved. The oceanic lithosphere is subducted beneath the continental lithosphere. The second continental plate will then bring the two continents together through the process of subduction. The continental lithosphere is not subducted because it is less dense than the oceanic lithosphere. This collision can cause the creation of mountains. This process has happened during the creation of the Himalayas and the Swiss Alps, the Appalachians, and the Urals. The picture you are currently looking at is a diagram of a hotspot. In a transform fault boundary, pieces of the lithosphere grind past each other in a horizontal fashion. They grind past each other in a way that does not destroy the lithosphere. Most transform fault boundaries usually join mid-ocean ridges. Transform fault boundaries that are active usually lie between the two offset ridge segments. Although most transform fault boundaries usually lie in ocean basins, there are some that lie on the continental lithosphere. One example of this is the San Andreas Fault in California. The picture you are currently viewing is a diagram of transform fault boundaries. Hotspots are small volcanic regions that are usually a few hundred kilometers across. Hotspots form when hotter than normal mantle material, called a mantle plume, goes up toward the surface. Once the plume reaches the top of the mantle, magma forms. The result is a small volcanic region. Most hotspots have lasted for millions of years and are still active today.